I'm now delighted to welcome a guest speaker from Canada. Tony Poulin is Draft Service Manager at Canam Buildings, and today he will present outstanding projects such as the Deloitte Summit Tower.
Good morning, everyone. My name is Tony Poulin from Canam. Today, we'll have an overview of Canam, one of the largest structural steel joist and deck fabricator in North America, and a short case study of 3 typical high-rise projects we built in Canada and USA, and about the challenge we faced at drafting engineering. I have been working at Canam for more than 30 years at different positions. I am the drafting manager of a team of more than 400 draftsmen located in different countries. We have 10 plants located in Canada and one of our bridge plant in Northeast USA. Our main plant is located in St. Gideon, a small town about 130 kilometers south of Quebec City and 50 kilometers from the US border. The plant is 700,000 square feet and has 14 shops that fabricate our different products. We have a production capacity of 380,000 tons a year. We built in Canada and United States around 8,000 projects a year, from supply only, installed by others, to complete design and build packages, including conceptual design and installation. Canam was founded in 1961 as a joist and deck supplier. Now Canam offers a large range of different steel construction products. Our latest are prefabricated load-bearing light gauge stud walls and shear walls that speed up the erection of multi-residential buildings. Canam has its own trucks and trailer float that deliver all across North America. We also have 3 offices overseas, one in Kolkata, India, with 125 employees, where a 4th level is in construction in our building to add 75 more employees in the near future. We have an office in Manila in the Philippines with 60 SDS2 drafters. And we have an office in Brașov, Romania. Our main overseas office is in Brașov, Romania, with 435 employees. Located in the Transylvania region, it celebrated its 25th years in May 2023. In 1998, Canam was in need of steel detailers because they had several major projects on their radar for the years to come. Several projects required hundreds of draftsmen. We had projects requiring more than 70,000 hours of detailing each. The Romania operation started with 15 people who were trained to steel detailing, and the office grew in number quickly. Today, the engineers and drafters at this office work on the drawings of all the product Canam provides. In 2002, Canam relocated from a rented downtown office to the south of the town in a new office they built and own. It's a 4-story building and all of our 435 employees work there. We offer several steel products, all related to the construction industry, and some have been developed by Canam and are registered mark. We provide all kinds of steel buildings from small ones to large sports stadiums. We built bridges too. One is in progress that will replace the bridge between Windsor, Ontario and Detroit, the busiest bridge between Canada and the United States. Our Muroc system is a complete prefabricated walls that include all the material from interior to exterior finish, including windows and doors. Our first case study is a complex high-rise we built in downtown Vancouver, the Deloitte Summit Tower. This building was made of several cubes oriented in different directions. The detailing of this project was done using SDS2 with our drafters in Manila, Philippines at 85%. 15% of the remaining detailing was handled in Quebec City. Almost all the steel was fabricated in Quebec and shipped to Vancouver. There were 5,680 imperial tons of steel for 24 stories. The cubes that ran 4 levels high each were aligned in different directions and independent from each other. Some of the outrigger parts of the bottom of the cubes were made of a glass floor. The roof of one cube was the floor of the upper one. 2 tower cranes were required for the erection of this building. The geometry was complex. There are just 6 steel columns that run from the ground to the roof, in orange on the sketch. These columns were W360 by 1,299 kilograms per meter, the heaviest W360 shape available in Canada. The concrete core stabilizes the building, while the 6 mega columns support the building. The color yellow represents the transition area, the roof of the lower cube. The principle was the same for each cube. Each 4-story high cube was supported by a truss each side of the cube. Here we see an ISO view of the SDS2 model of 6 cubes that shape one level of cube. Huge embedded plates and anchors in the concrete core supported the beam to which the 6 mega columns were attached. Mega columns needed to be attached to the concrete core before the cubes were installed. The stairs fit tight between the cube's support and the concrete core. All the stairs were modeled and included in the SDS2 model. The beam were attached with Dewey-Dag anchor that goes from one side of the concrete to the other side of the concrete for support. The detailing of the 4-level trusses was difficult because there was a huge camber to take into account. We detailed the trusses flat in SDS2, and with the help of construction lines, the diagonals were detailed shorter so they fit the camber before it's going down after the dead loads were applied. We use hydraulic jacks to support the cube temporarily. The jacks were progressively removed as the erection went on. Here is a truss diagonal that is being erected close to a mega column. Of course, because of the depth of the trusses, 4 levels, all their components were field bolted. The node at the bottom of the trusses were complex to detail and to fabricate. And there were no support under the truss first diagonal since the cubes were cantilevered. The top nodes were a bit less complex to detail. The mega columns had to rotate to suit the lines of the cube. The shop drawings of the nodes required a lot of views to make sure they were fabricated correctly. We worked with contact points instead of axis and center lines, and it ended up to be a good decision. It was easier in the shop and the nodes fit well on site. We also needed to indicate the order and procedure of assembly to make sure nothing was in the way at the moment of welding each plates of the nodes. Teamwork was required to make a project as complex as this one. The engineer, detailer, project manager, and shop manager met every day and with the help of the 3D model, made this project a success. We have another project based in downtown Toronto and it's in progress. It's 141 Bay Street, CIBC Square 2. This is a 56-story building in the heart of the city. The main challenge of this project was the fact that it's built above the Toronto train tracks and the city doesn't want to stop the train operations. It's quite a challenge for erection, and the base of the building needs to be smaller than the main building to clear the train tracks. So the lower columns are skewed to start with a small base and allow for a larger footprint above the train track. This project is detailed with SDS2 in our overseas offices and in Quebec. The model is so huge that we separated it in 4 parts to ease the navigation and the transfer between offices. For the last 2 years, though, we have used virtual desktops so all of our offices have access to the model in real time. No need to copy the model from one server to another. Manila is the last of our office where VDI will be installed. So for all the next major projects, we'll work in real time in all of our SDS2 model. The lower floor above the train station needed to be erected just between 1 a.m. to 4 a.m. while the train was not in operation. After the 4th floor, the city allows for erection during the day. They consider that 4 levels of floors would shield the track. The unloading area is small, which requires a lot of transportation logistic for a project of this magnitude. One of the last projects I'll talk about, we had a challenge with the 3D modelization. This building is 18-story high and it's located in the city of Portland, Maine. At 18-story, this building is the tallest in the state of Maine. The important fact here is the difference of columns' wide flange shape that support the same beams. This is where the challenge came from. The heaviest columns were W14 by 665 pounds per foot, surrounded by light W10s and W12 columns. There was no concrete core in the center of this building. The core was made of massive steel shapes. Because high-rise steel buildings are very heavy, the lower steel shrinks and shortens due to the dead weight coming from all the steel above. We are used to deal with these kinds of particularities with high-rise buildings. But in this case, the columns of the core were so massive that they did not shorten, while the smaller adjacent column did. So how can we handle that with a 3D model? If we detail the steel flat, the column that shortened would be fabricated too short. If we detail it with different ratio of shortening, we'll end up with sloped beams that are not sloped in reality. So we had to graphically modify the columns after our 3D checking process. By doing that, we kept the data of the 3D SDS2 model intact for the transfer to our automated equipment and robots, and fabricated the pieces long enough to suit the shortening. This is the tip we found to make everything work. Today, the 3D modelization does not automatically allow to handle these challenges, the steel shortening and the camber. We need a ghost model for reference or to work with construction lines to make it work. The model is the source of truth, either before the steel falls into place or after, but in between, we need to use tips and tricks to manage a fabrication that will suit different movements while erecting the steel. So I hope you found this presentation informative. Thank you for your time.
Thank you, Tony. That was a fascinating insight into these projects and the challenges in structural drafting and engineering.